If x plus 1 is 2003, for what positive integer k will x squared plus x be equal to 2003k? Well, the first thing I think is to factor out this x on this side. So that would be x and x plus 1, I guess. And then that just becomes nothing. It doesn't change. And then we take the fact that x plus 1 is 2003 and sub in here. So that would be x 2003. Okay, so that basically means that since we have 2003 on both sides, you can drop them, so x is equal to k. Then we'll take this guy to actually figure out what is x. If x plus 1 is 2003, that means x is 2002. So what are they asking for? They want you to figure out the value for k. Well, k is equal to x, and x is equal to 2002. Three circles with collinear centers are tangent as shown, and the radii are in the ratio 1 to 4. The distance from the leftmost center to the rightmost center, 72. What is the area of the smallest circle? Let's draw that connection. So there we go. And then let's label it. So this, based on this ratio, this radius would be x, this would be 2x, this would be 2x, this would be 4x. So the full would be x plus 2x plus 2x plus 4x. And they're saying that is 72. Okay, so this looks like 9x to me is 72, therefore x is 8. And they want you to figure out area of the smallest circle. So this circle, the area would be pi, well, the area of a circle is pi r squared, where r is the radius, and in this case the radius I've labeled as x. So it would be pi x squared. X is 8. So that looks to me like 64 pi. If x is equal to 3.14159,265, what is the sum of both values of x for which the absolute value of 3.14 minus pi plus the absolute value of 22 over 7 minus pi is equal to x minus 22 over 7, the absolute value of that? So let's do this carefully. This is going to be negative, so therefore it will be the equivalent of pi minus 3.14 when you drop the absolutes. This, I believe, and you can verify this in a calculator, is going to be positive, so that just stays as 22 over 7 minus pi when you drop the absolute sign. And x I don't know, so interesting. X I don't know, so if x minus 22 over 7 is greater than 0, greater than or equal to 0, I guess, it would be this. And if x minus 22 over 7 is less than 0, then it would be 22 over 7 minus x. Okay, I got it. And then this side all remains the same. Pi minus 3.14 plus 22 over 7 minus pi. Okay, so I got it. So I got to do this twice, and that's why they have the word both there. Okay, shouldn't be a problem. So let's see here. That cancels with that. And therefore, what else? Anything else cancel? I don't think so. So this becomes x is equal to 22 over 7 plus 22 over 7 minus 3.14. And that looks like 44 over 7 minus 3.14. We'll call this x1 since there's two x's. The next x is over here. So again, this cancels with that. And then this becomes 3.14, right? When you do the algebra, we'll call this x2. So they want the sum of both values. So x1 plus x2, so that's going to be 44 over 7 minus 3.14 plus 3.14, and that, of course, is just 44 over 7. So that is the final answer. What is the probability that when two different integers are chosen at random from the first 1,000 positive integers, their sum is even? Okay, so we have to talk a little bit about parity here before we get started. So if we have an even number plus an even number, that result will be even. So for example, if you have 2 plus 4, that's 6, right? And then if we have an even plus an odd number, that result will be odd. So for example, 2 plus 5, that's 7. And then if we have an odd plus an odd, that will be even. So for example, 3 plus 5 is 8. Now what they're saying is that they want us to figure out when the sum is even. So they want these scenarios. Okay, I think I can do that. So let's see what happens here. So I want first an even and an even. So the probability of choosing this guy from a pool of the first 1,000 numbers, so 1, 2, all the way till 999 and 1,000. Okay, so half of those are going to be even. So half, I'll just put it as 500 over 1,000 to choose this guy. And then I have to choose another one. Okay, so I've got to multiply it, but that's how probability works. Because it's this and that. Okay. So the next one, since one number has already been chosen, I've only got 999 left. And since one even number is already chosen, I've only have 499 even numbers left. Okay, so that takes care of this and this. And then the result will be even. Then we also need to figure out this scenario. It could be this or this. So when you have an or, you add a positive sign. So then we want an odd number. And an odd number of the 1,000 numbers, there's 500 odd numbers. And after you choose one odd number, there'd be 999 numbers left. And from those, 499 would be odd. So this is the full probability. I guess we just have to do the algebra. So this actually narrows down to 1/2 times 499 over 999. And this is 1/2 times 499 over 999. So then if you add this up, this is just 499 over 999. And that is the answer. "20 dancers line up one behind the other. At every clang of the cymbals, the dancers in positions 10 and 20 dance forward into positions 1 and 2, respectively, while the other 18 keep their same positions relative to each other. What is the least number of times that the cymbals must clang for the dancer originally in front to return there?" Oh boy, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so this is the original order. And so this is the start, I guess, right? And the original, the position of the first dancer, I'll put here. So as you can see, the position is 1, but nothing's happened yet. Okay, so then we got the first clang. So the clang, I guess the banging of the cymbals. So clang 1. When that happens, everybody switches. Well, not everybody, sorry, not everyone. Only the dancers in the 10th and 20th position. So this one and this one, they move forward into positions 1 and 2. So 10 goes into position 1 and 20 goes into position 2, and then everybody else moves forward. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is already taken. 11, 12, 13, 14, 15, 16, 17, 18, 19. And as you can see, 20 was already taken as well. So that happens, the first clang. Now, what's the position of dancer 1? Because what is the least number of times the cymbals must change for the original, for the dancer in the original in the front? So the front dancer is basically this guy right here. Now, where is he now? He's here. So that would be, he's in position 3. Okay? So this is the position of dancer, the original, the dancer in the front, basically, however you want to call it. Okay, let's do this again. So now we have clang again 2, clang 2. This time the position, the people in position 10. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the 10th. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this is the 20th. So they go into the first two positions. So we have 8 and then 19. And then everybody moves forward. 1, 2, 3, 4, 5, 6, 7. 8's already done. Yeah, the 9. 10's already done. 11, 12, 13, 14, 15, 16, 17, and 18, because 19's already done. Okay, so then where's the 10th guy? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the 10th guy. And where's the 20th one? 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 20. Okay. So then let's figure out where's the position of the original, the person in front. It's here, so that would be the position 5. And then after Clang 3, 6 and 18 would come up front. 6 and 18. And then everybody else moves forward. 8, 19, 10, 20, and then 1, 2, and then so on. And then now the position would be, this guy is in position 7, correct? 1, 2, 3, 4, yeah. And then you just kind of keep going. Now, what's the goal? The goal is, let me see here. We want this position to eventually go back to 1. Yeah. So this was Clang 3. So we got to figure out at what Clang does it go back to 1. So it's extremely time consuming unless there's some shortcut, which I don't see. So the way this actually worked is at start we had position 1. I'm just repeating what I wrote up there. Clang 1, it goes to position 3. Clang 2, it goes to position 5. Clang 3, it goes to position 7. And then it just kind of keeps on going like that. And we have to figure out at what Clang does it go back to position 1. And so I'll write it out for you. You can do some of you probably could do this really quickly. So I'll just write out the positions. At Clang 3, at position 7. At Clang 4, position 9. Clang 5, it actually goes to position 11. At Clang 6, it goes to position 12. It actually does not go up by 2 every time, which kind of messes things up a bit. 7, 13. Clang 8, it goes to position 14. Clang 9, position 15. Clang 10, position 16. 11, 17, 12, 18. Clang 13, 19. Clang 14 goes to 20. And then Clang 15, it goes to position 2. 16 goes to position 4. So now it starts behaving as a jumping of 2 now. 17, 6, 18, 8, 19, 10, and then on Clang 20, it goes back to position 1. So the answer to this very time-consuming question is 20. The sum of 5 consecutive integers equals their product. What are the possible values of this product? So we have a scenario where we have 5 numbers, say A plus B plus C plus D plus E, and that equals A times B times C times D times E, like that, right? So I think this is just trial and error. I don't think there's any actual formula. So let's plug in some numbers. How about if they're all 1s? Well, let's see if this works. This side will be 5, and this side will be 1. So that's obviously, that failed pretty quickly. And then you kind of just go from there. Let's say you have a combination of 2s and 1s. Like that. Let's see if this works. 2 times 2 times 2 times 1 times 1. Well, this side looks like 8, and this is 8. So there you go. So like that. And I'll just give you the other ones. 3, 3, and then 1, 1, 1. That works. 3 times 3 times 1 times 1 times 1. That is 9 is equal to 9. And then the other one that works is a 5 and a 2 combination with 1s. So that'd be 5 times 2 times 1 times 1 times 1. And that is 10 is equal to 10. So the possible values of the product are 8, 9, and 10.